So in order to talk about irrational numbers, we need to start with talking about what a rational number is. So here I'm at Wikipedia, and under irrational numbers, it says, in mathematics, a rational number is any number that can be expressed as the quotient or fraction p over q of two integers, a numerator p and a non-zero denominator q. Since q may be equal to 1, every integer is a rational number. To make sure you understand what we just read at Wikipedia, I'm here at Math is Fun under rational numbers, and they say a rational number is a real number that can be written as a simple fraction, i.e. as a ratio. Most numbers we use in everyday life are rational numbers. Well, you're going to find out that that's not really true. But an example, it says 1.5 is a rational number because 1.5 equals 3 over 2. It can be written as a fraction, or they call it a ratio. 3 over 2 is 1.5. We're going to find out in a little bit that this isn't actually 1.5. It's 1 1/2. It's another fraction or ratio. So it says here are some examples. 5 as a fraction. 5 over 1. Rational, yes. 1.75. Now we'll get into this, but it's 7/4. Yes. Here's a decimal, becomes 1,000th. Yes. Here's a negative sign. We're going to be covering this. They say yes. We're going to say no. The square root of 2 as a fraction? No. Oops. The square root of 2 cannot be written as a simple fraction. And there are many more such numbers. And because they are not rational, they're called irrational. Another famous irrational number is pi. Pi equals 3.14, and it goes off into infinity. It cannot be written as a ratio. So it is irrational. So we're going to be getting into what it means to be irrational, what numbers are irrational, and it's not just pi and a few others. We're going to cover that. So we're back here at Wikipedia under irrational number, and we're going to see what they have to say about irrational numbers. It says, in mathematics, an irrational number is a real number. We're going to come back to this. They cannot be expressed as a ratio of integers, i.e. as a fraction. Therefore, irrational numbers, when written as decimal numbers, do not terminate nor do they repeat. For example, the number pi starts with 3.14 going off into infinity, but no finite number of digits can represent it exactly, and it does not end in a segment that repeats itself infinitely often. The same can be said for any irrational number. I'm going to repeat that. The same can be said for any irrational number. One more time. The same can be said for any irrational number. Going on, it says, as a consequence of Cantor's proof that the real numbers are uncountable and the rationals countable, it follows that almost all real numbers are irrational. We'll cover this. When the ratio of lengths of two line segments is irrational, the line segments are also described as being incommensurable, meaning they share no measure in common. Numbers that are irrational include the ratio pi of a circle's circumference to its diameter, Euler's number e, the golden ratio, and the square root of 2. In fact, all square roots of natural numbers, other than perfect squares, are irrational. In fact, all square roots of natural numbers, other than perfect squares, are irrational. So here we are digging in a little deeper on real numbers. And it says, in mathematics, a real number is a value that represents a quantity along a line. The adjective real in this context was introduced in the 17th century by René Descartes, who distinguished between real and imaginary roots of polynomials. So you can see they have a number line here. And we've got our whole numbers, 1, 2, it's divided, there's 1 1/2. Now we've got the square root of 2 placed along this line. We've got e, we've got pi. We're led to believe that these are real numbers because they squeeze them in to these spots. Now the controllers of this world have set this up. They've created the label real number because when I go into explaining irrational numbers, I'm going to want to say that they're not a real number. But people are going to say, no, irrational numbers are real numbers. by definition, it says they are a real number. So I'm going to have to use a different term, and I'm going to use buildable or constructible when I'm talking about whether or not a number is real, and not be using this definition here. So the first problem that we run into with irrational numbers is they're not buildable or constructible. Now, I'm a carpenter and I work with wood and metal. If I'm cutting off a board with a saw, I'm usually trying to work to a 1/16 of an inch tolerance. If I'm doing fine woodworking, I'm working more in like a 1/32 of an inch. Now, if you want to make something more accurate, then you have machinists that do that. So I have machinists making most precision cut. Here's some images of the types of tools, things that machinists are using to make these fine cuts. And this right here is a process of tolerance that shows how accurate they can be. So you have traditional processes, non-traditional processes. This chart at the bottom here is tolerance in millimeters. And you can see it goes down to 0.002 millimeters. And none of these non-traditional methods go that far. And there are some traditional methods that do make it that far. But beyond that, you can't, there's no finer tolerance. That's the limit of what we have right now. So I want you to consider something. So what if you asked the best machinist in the world with the best tools to cut you something off at pi 3.14, a number that goes off into infinity, not repeating? Well, at some point, wherever he cuts, he's going to terminate this infinite series of decimals here. And as soon as he cuts and terminates it, it's become a fraction. There's no possible way that you can cut off an irrational number without turning it into a fraction. There's no way that you can build something that's an irrational number. You will have to make it a rational number that's going to be an integer, a fraction, a whole number and a fraction. That's the only way you can build something in this world. You cannot build something that's irrational. This is a very important concept to get in your head, because what we've been told from infancy is that the numbers are perfect and that we as humans are the failure. That the reason why we can't cut something off at 3.14 going off into infinity is because we're flawed, but the number itself is perfect. This doesn't make any sense. There's no possible way that you can cut something at a number that goes off into infinity. You cannot build it, not as that number. You have to terminate it and turn it into a fraction. Then it's buildable. So if you understand this flaw in irrational numbers, it might make your brain crash because it's not rational. And we're going to be getting into that. But what I'd like to do is read the story of the dangerous ratio. This is on Enriching Mathematics, and it says, "It's a stormy day on the sea off the coast of Greece. The date is around 520 BC. Fighting for his life, a man is heaved over the side of a boat and dropped into the open water to die. His name is Hippasus of Metapontium. His crime? Telling the world a mathematical secret, the secret of the dangerous ratio. The murder of Hippasus is a matter of legend, but the secret was real and certainly dangerous enough to be to the beliefs of those who knew about it. It was a secret owned by the school of Pythagoras. These early Greek mathematicians, Pythagoras himself was born around 569 BC, were obsessed with the significance of whole numbers and their ratios. The Pythagoreans' motto carved above the entrance of the school was, 'All is number.' Now, for people that know what I'm talking about and know that I believe that this is a simulation, I think Pythagoras might have been onto something, that all is number. But it goes on, the inner circle of the school, the Mathematici, believed that the universe was built around the whole numbers. Each number from 1 to 10 was given a very special significance. Odd numbers were thought to be male and even numbers female. Yet there was one number that the Pythagoreans found terrifying, the number that might have cost Hippasus his life for revealing its existence to the world. The name Pythagoras these days is best remembered for a geometrical theorem, the one that tells us how to calculate the lengths of the sides of a right-angled triangle, and it is from this theorem that the dangerous ratio emerges. Imagine a simple square, each side 1 unit in length. How long is the square's diagonal? This seemingly harmless question was the trigger for the Pythagoreans' disturbing discovery. The length of the square's diagonal is easy to work out. It forms the long side of a triangle with a right angle opposite, and two other sides of length 1 unit. Thanks to Pythagoras' theorem, we and the Greeks know that we can work out the square of the length of the longest side of a right-angled triangle by adding together the squares of the other two sides. So we know the diagonal length squared is 1 times 1 plus 1 times 1 equals 2, making the length of the diagonal itself the square root of 2. The numbers which, when multiplied by itself, makes 2. But what is that number? The square root of 2 isn't 1, because 1 times 1 is 1, and it isn't 2, because 2 times 2 is 4. It's something in between. This wasn't a problem for the Pythagoreans. It was obviously a ratio of two whole numbers. They only had to figure out what that ratio was, or at least that was their theory. But after more and more frantic attempts, a horrible discovery was made. There is no ratio that will produce the square root of 2. It simply can't be done. It's what we now call an irrational number, not because it's illogical. That's exactly what it is, but because it can't be represented as a ratio of whole numbers. This is what sent the Pythagoreans into such a spin that they may have sacrificed poor Hippasus. If you believe that everything is constructed from whole numbers, it is a terrible shock to discover that there is an everyday number, a real-world number like the diagonal of a square, that doesn't fit your picture of the world. It's a nightmare, and one from which the Pythagoreans would never really recover. So they go into a proof here, and for the sake of people that are watching this on their cell phones, I'm going to make a slideshow so that you can see this as I work through this problem right here. So what we're going to do now is take a look at the Pythagorean theorem. A squared plus b squared equals c squared. And we're going to take a look at using sides of 1. So this is a square, each side is 1, and we're going to be trying to figure out what c squared is. So 1 squared plus 1 squared equals c squared. Now 1 squared is 1, so 1 plus 1 equals c squared, or 2 equals c squared. So the square root of 2 equals c. Now if you pick up a calculator and do the square root of 2, you're going to get this answer, 1.414, and this number does go off into infinity, just like pi. Now we're going to do the proof of irrationality. So the square root of 2 equals the top integer over the bottom integer. And we're going to state here, we will state by definition that the ratio of or fraction must be reduced, taking out any common factors. An example of this is 2/4 must be reduced to 1/2. So let's square both sides of this equation to get rid of the square root. We've squared both sides, so now the 2 is free, and it equals top integer squared divided by bottom integer squared. Now let's multiply both sides by the bottom integer squared, which gives us 2 times bottom integer squared equals top integer squared. This means that top integer squared must be an even number, because 2 times anything is even. And that makes top integer, without being squared, an even number 2. Because an odd number multiplied by itself is always odd. So the square root of 2 equals top integer even, We know it's even. So 2 times bottom integer squared equals top integer squared. What's more, if top integer squared is an even number, so is bottom integer squared. This is because an even number squared divided by 2 is still even, and bottom integer squared is top integer squared divided by 2. So take a look at that formula down there. 2 times bottom integer squared equals top integer squared. What we're going to do is divide that by 2 on each side. So there's the bottom integer squared equals top integer squared divided by 2. So now we know that the square root of 2, we're looking for a top integer over a bottom integer. We know they're both even. That makes bottom an even number. So top and bottom are both even. That means that each of them can be divided by 2. But hang on. We started out by saying top and bottom were chosen as the simplest possible ratio. Any common factors had already been divided out. Now we are saying that they have to have a common factor of 2. That is not possible. So did your brain crash? It should have. If it didn't, maybe you didn't catch the problem. Go back, watch again. Because it's a logic error. A fatal exception has occurred. It's illogical. It's not possible. And that is a point that I'm going to be pounding home over and over and over, that things that are irrational are not possible. They're actually just figments of our imagination. If you look at this from a computer's perspective, when it's asked to do something that's not possible, it's illogical, it's irrational, it crashes. It can't do it. There's conflicting things that you're asking it to do, and it can't do it. There's a major problem here. Most of us have been taught from infancy that there's no problem with rational numbers. We haven't been told that it's illogical. We haven't been told that you can't make these numbers in the real world. But that is the fact. Some of these numbers have been raised to celebrity status. Pi and E and the golden ratio. Man, look at all the occult symbology that uses the golden ratio. This is another impossible number. It's irrational. You can't build it, and there's logic fallacies in it. It turned out that the school of Pythagoras, who thought that all was number, and were obsessed with the significance of whole numbers and their ratios, they were correct. Rational numbers are the only real numbers. Now, I'm not talking about the real, like the Wikipedia definition. I'm talking about real as in buildable or constructible, something that you can actually use. The problem is Pythagoras' theorem, a squared plus b squared equals c squared, gives you an irrational result every single time, unless if what you're taking a square root of is a perfect square. That's the only time you get a rational number. Any other time, it gives you an irrational result. Let's reread that sentence from Irrational Number on Wikipedia, where it says, in fact, all square roots of natural numbers, other than perfect squares, are irrational. Let's reread the first sentence of Irrational Number at Wikipedia one more time to make sure that you're getting the point. In mathematics, an irrational number is a real number that cannot be expressed as a ratio of integers, i.e. as a fraction. Fractions are the only numbers that are buildable or constructible. Okay, these are the real numbers. Therefore, irrational numbers, when written as decimal numbers, do not terminate, nor do they repeat. And then they give the example of pi. So over here, the mathematical constant pi is an irrational number that is much represented in popular culture. For those that have eyes to see, do you see how they've promoted this? They've made a deity out of pi. It's an irrational number. It's not a real number. It's not a buildable, constructible number. All right, so all the numbers that repeat, the 0.333333333, the 0.666666666, those numbers are irrational. And then the rest of the numbers that repeat, they repeat until infinity. They're not buildable or constructible. So this is literally the tip of the iceberg as far as the problems with math that I've come across. I had a bunch of videos up on my channel before when I first started diving into the problems with math. And I was doing everything on the fly. I took those videos down when I struck out against the popular flat earth model because I didn't want to be attacked on too many fronts. But it's been processing in the back of my head, these problems with math. I've been doing more research on it, and I'm seeing easier ways to describe the problems that I was seeing, and I think it's more relatable right now. So I want to get back into covering the problems that I see with math, and I'm going to try to keep the videos underneath a half an hour. There might be a bunch of them. There's a whole lot of this. The nice thing is that math is going to get a whole lot easier. We're going to be able to throw away all this garbage that we see on the screen right now. So, I look forward to talking to you more about this. Hope you enjoy it.